Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure today to introduce Jai Li to MSR. She is currently at Stanford, but I think had quite a trek with her advisor, Fei Fei, technically graduating from Stanford.
Yeah.
Right, yeah. But has also been to Princeton and University of Illinois.
Yeah.
And she's done a lot of great work in image understanding and semantics. She had a role in developing ImageNet and had a recent great work on image understanding called Object Bank, which I think she's going to be talking about today. Great.
Thank you. Hi, everybody. Today I'm going to talk about semantic image understanding from the web in large scale with real-world challenging data. As all of us know, a picture is worth 1,000 words. So humans can easily understand a lot of information from an image. For example, in this photo, two cat friends are sitting in front of a table, having fish and having a drink in a restaurant. The understanding has different layers. For example, there are objects involved. And seeing this is a restaurant, it's indoor, and there are activities. For example, these two cats are drinking. As easy as human can do all these tasks, computer has a long way to understand the same information. So we want to endow computer the same ability to understand an image at the same level as a human. So understanding an image as a human is an overreaching goal. It's a very grandiose goal. Let's see what's fundamental computer vision problems involved. It is related to classic problem object recognition. For example, find two cats here. And sometimes we need to give an overall label of the image. This is a dining image, and it's indoor. But only knowing the objects within an image or a global label of the image is far from enough. Sometimes we need to segment out the objects or grouping pixels belonging to one object. That is the segmentation task. And usually we want to connect the image pixels to semantic meaning. That's the annotation task. So here, the problem I want to solve is to endow the computer to understand every single pixel of an image. So why do we care about this problem at all? So first, in our physical world, vision is the most fundamental sensory for humans. 50% of our neurons are devoted for image processing. We use vision to read, to drive, to social, to work, and to enjoy our life. And visual intelligence becomes very important since there are vast amount of digital data, media data out there. We want to harness this vast amount of data to have a better understanding of our visual world. So my approach is I want to learn from real-world images, such as those ones on the internet, and in turn apply to real-world problems, such as robot navigation, perception, autonomous car driving, and sometimes we wanted to help us to build a safer world and automatically organize the vast amount of multimedia data online or in our personal albums. And we also want such technique to help us to do automatic camera calibration depending on what kind of object and what kind of scene we are shooting at. And it can also be used to improve our image search results. And eventually, we wanted to help the visually impaired or elder people to perceive the beautiful visual world. Here is an overview of my thesis work. Basically, towards the goal of understanding every single pixel, I have been working on object recognition, event recognition, image representation for understanding image, and hierarchy construction, and scene understanding. Today, I will due to the time limit, I will sample a couple of them and talk in detail. So I will first briefly introduce a new way to tackle a classical problem, object recognition. And I will briefly talk about a classical problem, image classification, by introduce a new image representation, object bank. And then I will talk in detail more ambitious and less investigated problem. That's the scene understanding. So let's start with object recognition. I'll talk about our 2007 and 2009 work about Optimal. It's an automatic object picture collection with incremental model learning. So let's look at the traditional problem of object recognition in recognizing a single class of object. Suppose we want a computer or the smart agent to find a cat within this picture. As easy as human can do this, this is a very challenging task for the computers. We are facing a lot of occlusions in this image, and it's in a cluttered restaurant, and there are uncertain lighting, etc. Literally, there are hundreds and thousands of papers published on this topic. There is one common property among all these papers that they need to start from some manually collected clean data. For example, here we are looking for a cat. Then we need to collect a cat dataset. And now we want to look for fish in this image. We need to manually collect a clean fish dataset to learn our model. And these are okay because they are in the Caltech 101 of Pascal dataset. We can easily use those images. Now, if we want the computer to look for a rare object, such as a Japanese wine cup in this image, we're in big trouble now. Where do we find our dataset? And this is a problem, is a bigger problem. Think about how many objects are there in our world, and how these methods be able to scalable to all these objects within our world. In this 2007 work, we try to harness the vast open internet and use the internet images to learn an object model. And it is scalable to any object that with images online. And now, internet is great. We can type in a word, keyword, for example, chicken, to all those search engines, and we can get a lot of images. But there are some challenges. For example, there could be multiple types of chicken, animal chicken, the cartoon chicken, etc. Existing methods, such as constellation models or parametric topic models, they have fixed complexity. You need to give a priori set parameter to tell it how many types of chicken are there. And this number of types will vary over different objects. So in Optimal, we try to use a non-parametric topic model, which is flexible in complexity. While I have no time to dive into details of the non-parametric topic model at a high level, basically it can offer natural clustering among all these images, and it will be able to capture multiple prototypes of the objects. So we are facing some other challenges. For example, there are many incorrect or irrelevant images, which we call is a very noisy internet is a very noisy library. Existing methods are normally limited to hand clean data, which again cause the human-labored clean data set. How do we deal with this? We use a noisy noise rejection system that is robust to noise. The idea is, while we are sifting through all the internet images, we only keep the good related images to learn our model while rejecting the noisy images. So here is a glance about our optimal system. Basically, starting from a very small handful number of seed images, which we can easily obtain from the first couple in the search engine. We can learn a model that can capture the property of the chicken object. Now, serving as a classifier, this model can go back to the internet and pull more relevant images to this model. And the good relevant images will be appended to the dataset, and it will be used to incrementally learn the object model such that we can obtain a larger and larger dataset while have a better accurate model through this incremental learning in a very efficient way.
Do you find that all that it restricts the variability of the images that you collect then? I mean, does it do a good job if you have a category which has a lot of different
Yeah, that's the non-parametric model about. So it can capture the variability of different prototypes.
So it does do a good job of capturing the variability.
Yeah. So later I will show some results related to that. So our system has been tested on large-scale datasets with no labeled images. It can accurately recognize and localize the object. Basically here, the purple bounding box is the localized object, and it has a label to indicate what kind of objects are these. We also compare the multi-way classification with some state-of-the-art algorithm. Again, no labeled data were used in this setting. And this goes back to the question that Larry was mentioned. Our model can naturally capture the multiple prototype about one object. It fits naturally in the polysemy interpretation problem. Suppose we type in mouse in the Bing or Google image search, we can get a lot of images about animal mouse, computer mouse, and some of them are not even related. Our model can naturally separate them into animal mouse, computer mouse, and discard the unrelated ones. So its superior performance earned us the first place in a competition that is designed to simulate the real-world robot perception scenario. In this AAAI and NSF organized competition, each of the team were given a list of objects. And then within very limited training time, say 2 hours for over 30 objects with a single machine. And the computers are required to learn the models for all these objects. And dataset is not available, but the internet access is provided. And the list of objects, object names were not provided before the competition. Now, do you feel this is a very familiar setting? It's basically the optimal setting for our framework. Our computer can then go to the internet and collect a lot of related images to each of these object concepts and learn a good model that can capture all these properties from noisy internet images and eventually correctly and accurately detect the objects within a cluttered conference room. So now let's switch gear a little bit and talk about a classical problem, the image classification problem. Here I'm going to introduce our image representation called the object bank. As we know, image classification is a very challenging problem, especially when the classification is related to semantic meaning. For example, this image is a sailing event. And similarly, this image is similar in appearance and it's also a sailing image. But sometimes the appearance could be quite different. For example, the color in this image and the layout of this image is pretty different than the previous two. And sometimes it goes too challenging and it's impossible for a computer to detect it. This is an on-boat shot of a sailing image. Apart from some similarity in some small patches of water and sky, there is very little similarity in appearance to the previous two. And traditionally, people were using low-level features to describe all this kind of appearance. Low-level features actually carries very little semantic meaning, causing the so-called semantic gap to the high-level tasks. We need some good and semantically meaningful representation to close the semantic gap. And as we know, objects could be very useful in complex scene recognition. Let's go through a very simple thought experiment. We are using the UIUC sports event dataset as an example. It's an 8-event class dataset with very complex scene images. And the best low-level image representation, the spatial pyramid matching with SIFT feature, can achieve about 70% on this dataset. And suppose somebody magically give us some object labels related to each image. How much can we achieve in the classification? 100% in this experiment. There is a huge gap between the low-level image representation and the ideal high-level image representation. How do we obtain this kind of high-level image representation? We introduce the object bank, which encodes the spatial location of the objects and the possibility of the objects appearing in some image, in some scene image. Starting from a scene image, for example, this sailing image, let's try to obtain the possibility of sailboat appearing in this image. So we run some object detector for sailboat on this image. And different objects have different spatial preference. For example, if I say, look for sky, most of us will look up. And things like water always appear at the bottom of the image. So we pull the maximum value of the object probability from a spatial pyramid structure that can capture all this spatial preference. And the object size could be very different. The same horse object could appear at different size in different images. We run over different scales our detectors. And we want to describe multiple objects, their possibility appearing in one image. So we run up multiple detectors over an image. And that's our final object bank representation for an image. Specifically, we use around 200 object detectors. And these 200 object detector names are summarized from famous image dataset, the language corpus analysis, and image search result. And we had around 200 object detectors around NIPS time, and now we have around 2,000.
Sorry, where did you get the categories from?
The categories, basically, we use the WordNet to get the object names, and then we try to find what's the most popular objects and what's the most important objects by using the statistics from image dataset, from the language analysis, and web images statistics. Yeah. So what's so special about object bank representation? Let's see these two images. Human will have no problem to differentiate them. One is about mountain or forest, and the other is an inside city image. But let's see from the low-level image representation point of view, the just filter bank-based representation. They look almost identical on these two images. And the best state-of-the-art image representation, SPM, SIFT, they also look very similar to each other. Now, let's see the object bank representation. As we can see, the tree response, the possibility of tree appear in this image is very high, and is very low in the other image. So from the appearance, we can easily differentiate these two images by using object bank. As a proof of concept, we apply our object bank representation to scene classification. Let's start with a very simple, basic level scene classification. The low-level image representation can achieve about 50% around that range. And here, we use a very simple off-the-shelf object classifier, the linear SVM. Object bank can achieve much better results over the low-level image representation. On a more complex scene class dataset, that's the MIT indoor dataset, the advantage of object bank is more obvious. It outperforms all the low-level image representation, and it outperforms the state-of-the-art, which requires more human supervision than object bank. And similarly, for superordinate complex scene classification, our object bank again outperforms the low-level image representation and the state-of-the-art representation, a state-of-the-art approach. What's the take-home message? Basically, this means with the more descriptive image representation, the burden of designing a complex model can be reduced. And if we combine the powerful image representation with some more sophisticated modeling, we can achieve even better results. And when I introduce the object bank representation, I brushed aside the fact that it is a very high-dimensional representation, which can easily lead to problems related to curse of dimensionality. So the good news is it's a high-dimensional representation with redundancy. As long as we find an effective way to remove the redundancy and keep the useful information, then we can still achieve a good compression on this image representation. So we choose to use regularized logistic regression to compress object bank. For those of you who are not very familiar with this regularized logistic regression, here is the objective function. Basically, the first term is, if we only keep the first term, it will be the vanilla logistic regression for classification. And the regularizer we put here is basically try to help us, try to encourage the important objects at important scale and important locations to be selected. For example, in this setting, for sailing image, sailboat response and the water response will be selected, and the water response at the lower part of the image and sailboat at the middle part of the image will be selected. In this way, we can compress object bank to 1/10 of its original dimension, and the classification performance is still on par. And further, because this compression is based on semantic meaning, we can discover some good interpretability. Let's look at that.
On the previous slide, I missed the algorithm. How many different classifiers do you have?
How many different classifiers? So basically, it's one versus all. So basically,
if you have an image, you run all these different keyword classifiers on it. You have thousands of keyword classifiers.
That's when we construct the object bank representation, and here we already have the representation. So we just do a scene classification. So depends on how many scenes you have, then you have how many classifiers there.
But how do you decide to run bare response on here?
That's again from the object bank construction part. So basically, we try to summarize the important objects from the statistics we collected from important object dataset, from the image search result, from the language analysis. And we find, okay, not all the objects are equally important to each other. So we finally end up selecting 200 at that time, and it's 2,000 now. And now with that, we can represent our image as an object bank representation, and it will be the input for this classification algorithm. Yeah. Currently, we run 2,000. Yeah.
Can you explain the regularizer? I can understand the L1 term. What's the
regularizer? Basically, this L12 is a group-wise regularizer. It will encourage one group of dimensions. For example, the dimensions related to one object to be jointly 0. Yeah, and the second term is the sparsity, is the L1 regularizer. You will encourage the sparsity within the object, the group of non-zero dimensions to be 0. Yeah.
How do you optimize this function?
Just coordinate this descent. Yeah.
Do you do it this way mainly because that way it gives it some semantic meaning, or
Exactly.
does it perform better than PCA? Or
So
something else like?
we wanted to preserve some semantic meaning, and here I want to show that actually. So PCA won't be able to discover all this. So basically, the compression method is based on semantic. Let's see this speech class. We can from the human point of view, we can see that sky and water and sand and grass are very important objects within this speech class. It can be automatically discovered by our algorithm. Just the semantically based compression. It will keep, as I explained just now, it will keep the important objects at its important location and important scales. And similarly, for this mountain scene, we can find out that sky, mountain, and tree and rock are the most important object class. Now, we have the object, important object. Let's see their spatial important spatial location and scales. Basically, here we have a cloud. As we can see, cloud is around mid-size. It doesn't occupy the entire image, and it's not too small. And the location is always at the upper part of the image. This can be also discovered by the semantically based compression method.
One quick question. So, how important is that L12 term? I mean, I can imagine doing the same thing just with an L1 regularization.
L12 term will help you to discover the important objects.
Do you have any experiments where you just use the L1 term and did the same thing?
So we did 3 experiments actually. One is the L1 term. L1 term will discover the important dimension despite what objects it belongs to, right? The problem with that is it doesn't keep the structure of the object bank representation because we form the object bank representation based on objects, based on their spatial location, etc. And different objects have different probability to appear in different classes. So L12 is introduced just to capture the importance of objects.
Oh, we can take it offline.
Yeah, and okay.
Are you familiar with the class names work by Lorenzo Torresani?
Yeah, I know.
Can you just briefly state why
Okay.
pros and cons?
Sure. So I think that work is great. Basically, the major difference is we capture the spatial location of the possible object within an image. And we try to capture the semantic meaning, where they claim that it's an intermediate representation doesn't necessarily relate to semantic meaning. But with semantic meaning and spatial location information, you can see we can do a lot of interesting things. And we can build, in the future, we can build, say, segmentation algorithm based on the possibility of object appearing in an image from the responses of objects within an image. So there are a lot of applications for this. So, are we good? So, now I'm going to talk in detail a more challenging and less investigated problem, the total scene understanding problem. In total scene understanding, we try to understand every single pixel of an image. And currently, we're considering classification, segmentation, and annotation. As we know, traditionally, these 3 problems are independent, separate fields in multimedia and computer vision. And they have been treated as independent problems. Here, we try to solve them together towards the goal of total scene understanding, taking advantage of the fact they are mutually beneficial to each other. And traditional methods also require clean training data. Here, we'll try, similarly as our optimal approach, we'll try to learn from internet noisy data such that we can release the human labor from this heavy labeling, because segmentation and annotation actually requires much more labor work than labeling the object within it. So how do we model these 3 problems? First, we want to model the classification. Here we use a generative model, which is represented as a graphic model here. Circle represents a random variable, and plate represents repetition. I'll gradually build upon this simple model to achieve the end goal. So C here is an image class. It can take values such as polo, sailing, rock climbing, etc. It's slightly shaded. That means it's observed in training. And we also want to do segmentation. How do we do that? We pre-segment all the images based on low-level cues into coherent segments. And the problem is we don't know which segment belongs to what object. We use an object, O variable, to represent here. O can take values such as horse, grass, sky, etc. And different objects, the possibility of different objects appearing in different image class is quite different. We use a multinomial distribution to model that. And the object identity is related to its appearance. For example, horse is always sometimes brown, and its texture is like this skin-like texture, while grass is always green, and the texture is the needle-like texture. So we use color, location, texture, and shape to represent our appearance, region appearance. And different objects have different appearance. So we model this as a multinomial distribution given the object. And small regions, small patches within each region can sometimes to be very discriminative. For example, the knees and the ears of the horse can help us to differentiate it from other objects. So we model, we extract the SIFT representation to represent these small patches. And the model is as a multinomial distribution depending on the object. And now, this is the visual component. And we want to model annotation as well. We want to connect our visual regions to the annotation words. So T here is also, again, observed in training. So we have, as we know, that the number of segments in the image and the number of text words are quite different. So we use a connector variable to associate the text word to one of the image regions. And there are also some visually not related text words, such as saddle, but it can help us to differentiate the polo class from some of other rock climbing classes, etc. So we use a switch variable to connect these visually less salient or visually unrelated words to the class variable. If it's visually very salient objects, such as horse and human, we connect it with the object within the image. So the exact inference of this model is intractable. I derived a collapse Gibbs sampling method to do all this. Again, here we try to learn from internet data because we already modeled the visually unrelated text and the visually less salient text. So no human supervision is needed. We can go to Flickr, Picasa, and Windows Live to grab a lot of user images and try to learn from there. So, for example, here we tested on Flickr user data. We downloaded 8 event scene classes. Here, each doublet represents the images from one class. We can see this dataset is a very challenging one. Objects can be very blurred, and there are occlusions, and there are multiple objects, etc. This is also a quite large dataset. It's over 600 images and over 1,200 concepts. Now, I have talked about we have 3 goals. Now let's evaluate the performance on this 3 individual goals. So let's start with the classification task. So here we first compare with Fei and Cao. They are visually only based model, pioneer topic model, language model that has been applied in scene classification. They can achieve about 40%. And now, let's see another model that jointly models the textual component and the visual appearance. It can do slightly better. This is the performance of our model. By jointly modeling the textual and visual appearance and considering capturing the noisy property of internet data, we can achieve a much better result. And,
How are you doing the classification in your model? I thought it's a unsupervised way of finding segments, and how are you modifying it to do
so
classification?
the scene class I mentioned in the model, the C variable is observed in training, so we can predict it in test.
So in test, you basically hide it,
Right.
and then you're trying to infer what's the most likely.
Exactly. Yeah. So in annotation, we try to compare with the traditional, very, very popular multimedia content-based annotation, Aliper. And a joint, as I mentioned just now, the joint modeling of textual and visual appearance. They are doing comparably well. And our method, by jointly modeling the textual and visual appearance and considering, I think the most important part is considering the noisy property of the internet images, we can achieve much better results. Here is the overall result. And in segmentation, we compare with the state-of-the-art concurrent object segmentation. Basically, you concurrently segmenting multiple objects from in an image. That's the Cao et al. And our model can do better in every single class, object class. Now let's see some visualization results. How can we segment this image? What's the most challenging object here? Probably the snowboard. Let's see if we can get it. Yes. Although it's a very small object and it has this different viewpoint, etc. By learning from large amount of internet images, we can, and modeling the internet image property, we can successfully model it.
And what was the input for the algorithm here? You just said
Flickr images and tags in training.
right, but when you ran the segment, you just said snowboard to the system, and it. And it
Basically,
highlighted that.
this is the input is just one image
One image and
with no tag
with no
in
tag.
test, with no tag.
Right.
But because we model the tag relationship and the visual relationship and the class relationship so well in training phrase, it can capture it when you feed in unknown image to it. Yeah.
The output is not just snowboard.
It's not. I'm going to show.
What's the base level segmentation are you using?
Base level.
I mean, you mentioned that the input is not just raw pixels, but some
Coherent
segmented.
small segments.
Yeah,
Yeah,
so for
then you can use any low-level segmentation algorithm. Specifically, we were using SuperPixel, the Pheasant swab algorithm.
Just on the RGB values?
Just based on the local appearance, low-level appearance, yeah. We can also detect human. And sky, cloud, snow, and trees, all concurrently, automatically done. And now, a more challenging task to segment out the objects. As we know, segmenting horse is a very popular topic. There are hundreds of papers published on segmenting horse. And there are even datasets, just human labeled dataset developed just for this object. our segmentation algorithm can successfully segment the object concurrently with some other objects as well.
But a lot of that is actually dependent upon your superpixel segmentation algorithm.
Oh,
Because a lot of times, like the socks of the horse is always missing. So
exactly. But if you take a look at the original superpixel input, it's very over-segmented. It doesn't have semantic meaning at all. Then you need to put together all the segments related to some objects. That's a very difficult part because the low-level segmentation doesn't carry any semantic meaning at all. Yeah. So further, let's see some segmentation and annotation task. Basically, given this image, our algorithm can perfectly segment out the objects within it. And in addition, we can discover some visually not so salient objects, such as wind and seaside. It's because they're so related to the salient class, they can be automatically discovered as well. This is largely attributed to the switch variable that can selectively associate one text word to the visual content or to the image class. If we try to associate wind to some visual appearance here, we'll be in big trouble. Yeah, so understanding one image is very good. We can do a lot of things: segmentation, annotation, etc. And now, what else can we do? We can do some fun application. For example, organizing many images. I don't know about you, but I'm a big travel fan, and I take a lot of pictures during my travel. And I'm also a very lazy person. I do the minimum part of organization after my travel. Now, this is all the folders containing my images. Suppose one day my friend come to me and ask me to show her all my birthday party photos. I will be in big trouble. I'll have to go into each of these folder and try to find my birthday party photos. How tedious is that? This can be done easily and automatically by building upon the total scene multimodality model and impose a hierarchical non-parametric prior on that, which is a nested Chinese restaurant process. Don't worry, I'm not going into detail of this. But if you want to discuss offline, I'm happy to talk about details. And let's see, what can we do with that? All the photos will be grouped as photos. And then within photos, we can see event photos. And wedding photos are grouped as a sub-part of event photos. And within wedding images, we can see wedding gown and flower images related to wedding. And we have birthday images within event. Many other branches containing different concepts. And within them, there could be garden and holiday, etc., etc. The most important thing is all this can be done automatically. So I've talked about.
You say it could be done automatically. Have you built this system, or this is something?
This is already done. Yeah.
Okay. And where is this described?
Huh?
Which of your publications describes this?
It's my 2010 CVPR publication. So I'm happy to talk more about that. I've talked about my current effort. So in the future, towards the goal to semantic image understanding, a detailed understanding of every single pixel within an image, I want to develop a more powerful image representation. Remember, previously I mentioned about the object bank. It's a very good representation, the problem is its high dimensionality. And we used the supervised method to compress it. And it was effective. But sometimes we don't want supervision. As we know, unsupervised feature learning has been very successful recently. Why don't we just use unsupervised feature learning upon object bank representation to discover the useful representation while preserve its original structure and original object meaning? That's one of my short-term goal. And in the long term, as we know, there are large-scale multimedia data available online. I'm sure Microsoft have a lot of them. So the question is, how are we effectively take advantage of this data, such as GPS information, timestamp, the user tags, the text information around some images? I want to do a good analysis and to integrate all these components and let them be mutually beneficial to each other and help us to manage this multimedia data better in the future. And a more ambitious goal is to use image as information source to understand human behavior and society. As we know, different generation might have different flavors of images that they want to browse. A little girl would browse a lot of Disneyland images, and travel fan or snowboarding fan will have a lot of snowboarding images in their personal albums. So this will reflect their behavior, and we can, based on that, to form useful groups or societies among them, and also maybe to recommend different products to them. Yeah. So in my research, my goal is to understand every single pixel within an image. I've talked about a new way of tackling a classical problem, object recognition, by learning from noisy internet images, where no human supervision will be required. And this algorithm will be scalable to recognize any object with images online. And I've also introduced the new image representation for classical problem, image classification. And it's a sharp departure of all the low-level image representation by carrying rich semantic meaning and close the semantic gap. And finally, I talked about the total scene understanding problem, a very ambitious and less investigated problem. And this is our first attempt to understand every single pixel within an image. And again, we try to learn from the real-world images and try to recognize real-world challenging images. That's the end of my talk. I'd like to thank you, everybody here, and thank all my collaborators and funding resources. Yeah. Hi.
How would you improve image classification using object banks? I mean, there's still some ways to go.
Exactly. So there are two ways to go. So as we know, two important components is the image representation, and another important component is how we use model to capture the information that is carried by the representation. From the representation side, as I mentioned, I want to improve it basically from make it more efficient and compact representation, and also we can improve the object recognition result so that the image representation built upon it will be more robust. That's one aspect. Another aspect is, suppose we have the representation here. How are we going to take advantage of the existing representation and extract the most useful information, useful components from it? So two of my other approaches are kind of that flavor. Basically, you use them good machine learning algorithm to capture the properties that is embedded in the image representation, so that to achieve a good representation, achieve a good performance in image classification. Yeah.
Okay, so I'm kind of curious, like, you know, in all, what is the most common failure mode right now as an object bank?
You mean most?
What does it fail right now?
So currently we have tested on all existing scene dataset, and we also tested it on one object dataset, the Caltech 256. I have to say, Object Bank actually has the most potential in recognizing object-centric or object-oriented images. So if, say, we are doing a image deduplication, I don't think we necessarily go that far in use object bank representation to do that. But if it's connected to semantic meaning and connected to objects, it's very powerful. So far we've observed that it actually gives the best result on the UI/UC sports. It's a very object-oriented data set, carries a lot of semantic meaning. Yeah. Did that answer your question?
We can do it offline. Not quite, but we can chat.
Because I think that just follow up on Signing's question, it's impressive that your system is the best, but even the best is only 60%. So which are the failures that jump out the most that you know? Where is it like, obviously a human has no problem, but all computers do?
As I showed just now, that human, if we can have the object labels, it can achieve 100%, right? Current part is the object recognition. Object detectors haven't been developed into that perfect situation. Once if we have a perfect object detection, that is basically a solved problem.
But if we have perfect object detection, it might be the case that what you put on top of it doesn't matter as much anymore. Because
yeah, exactly. So currently, it's what I show here is object detectors are not perfect, but as some intermediate representation, it can show a lot of potential in classification. Yeah.
I have a question about the first part when you do the text search and you retrieve internet images. Like, what is the algorithm? You type in a keyword, some images show up. Then how much data do you actually pick? When do you know that you have learned a model for a mouse?
That's a very good question. It's related to some technical detail. So basically, we collect all the possible images related to one concept, and then we do incremental learning.
Thousand images?
So I've tested on over 400,000 images, over 23 classes. Basically, the question is how, where should we stop? Right. So in the iterative learning process, we try to learn a good model while reject the bad ones. So we learn till we cannot get useful images. So till the model thinks, okay, there is no related images. All images are rejected. Then we stop. Yeah.
You didn't say much about the low-level features you use. So for the optimal system, where you're learning your hierarchical model of top features, and also for Object Bank, you have your initial filters.
Right.
So what are you using at the very earliest stages?
Very earlier stage. So in optimal, we use the SIFT image representation, and we show that with a good machine learning technique and a good vision algorithm, even with very simple image representation, you can already see very positive signal in object recognition. And in Object Bank, basically, it depends on what kind of object detectors or what kind of object filters we use. We use different type of low-level features. We have used color, texture, and we also used a hog feature within it. So basically, I I still think the low-level features are very useful features. Object bank is not designed to replace the low-level image representation. In fact, when we did some experiments to combine the object bank representation with the low-level image representation, and it shows significant boost over both object bank representation and the low-level representation. And that shows that object bank representation is a high-level, semantically based image representation. It's complementary to the low-level image representation. While when we do experiment by combining two low-level image representation, since, for example, gist and SIFT, their property are quite similar, so there won't many boost in that experiment. Yeah.
Let's thank the speaker again.
Thank you.